The last topic we will be covering in thermochemistry this semester is the concept of enthalpy. I'm going to attempt to explain enthalpy here in this video, but if you walk away still a little confused, don't worry about it too much. Enthalpy is a fairly abstract concept. While measuring heat is fairly straightforward, given we know the mass and temperatures of a system, we can use Q equals the SM delta T equation. So basically, by simply measuring temperatures, we can measure heat. Measuring work, however, is more complex. So we can simplify measuring the total change of energy of a system, the delta U, by introducing the concept of enthalpy and making some assumptions. Enthalpy is the measure of a system's energy, pressure, and volume. Determining the absolute enthalpy of a system is just about as impossible, well, it is as impossible as determining the absolute energy of a system. However, if we make a few reasonable assumptions, measuring the change in enthalpy becomes simple. First, we assume that pressure is constant. This is a valid assumption for any reaction done in an open container because there's nothing to trap the gas molecules and cause an increase in pressure. Also, there are many reactions that don't involve gases at all, so those would always be under constant pressure. Secondly, we assume the only form of work done by a chemical reaction is pressure volume work. There is some fancy math involved here that I'm not going to get into, but ultimately we come up with an equation that says enthalpy is equal to heat. We have to look at this just a little bit closer though. Enthalpy has units of joules per mole or kilojoules per mole. The unit of heat is just joules or kilojoules. Thus, the enthalpy of a chemical reaction is actually equal to the heat of the reaction divided by the moles of reaction producing that heat. This gives us an equation, delta H, the change in enthalpy, is equal to the heat divided by the moles. We add the subscript reaction, Rxn, to the delta H, here, the enthalpy sub-reaction, that indicates that it is the enthalpy of a chemical reaction. There are other forms of enthalpy in addition to enthalpies of reaction. One of the most pertinent forms of enthalpy is enthalpy of formation. This is the change in enthalpy that occurs when 1 mole of a compound is formed from its elements. It is symbolized with a delta H sub F, the change in heat when 1 mole of a compound is formed from its elements. These are standard values that you can look up. There's an entire appendix of them in the back of your textbook. For elements already in their standard state, the enthalpy of formation is 0. What do I mean by an element in their standard state or their elemental form? What that means is the way they would exist in nature at standard temperature and pressure. So we learned about standard states when we learned about the periodic table. Almost all the metals, their standard state is as a solid, except for mercury, whose standard state is a liquid. The noble gases exist as gases. And then we have a few elements that exist as diatomics. For example, H2 gas, N2 gas, O2 gas, F2 gas, chlorine gas, Cl2 gas, and bromine, Br2 liquid, iodine is I2 solid. So those are some examples of substances that are in their standard state. So since they're in their standard state, they're already formed. So there's no energy or enthalpy to form them. Okay. We can determine the enthalpy for a reaction theoretically by subtracting the enthalpies of the products from the enthalpies of the reactants, which is this equation here. The delta H of the reaction is equal to the sum of, so this little symbol here just means sum of, which we know in math sum is adding. So we're adding up the enthalpies of the formations of the products, and we subtract from that the sum of the enthalpy of formations of the reactants. When you guys use this equation, don't forget that a chemical reaction is reactants going towards products. One of the most common mistakes I see students make when they use this equation is that they put the reactants first and the products second because that's the order it is in the chemical reaction. But it should be products, which are second, minus reactants, which are first. The reason for this is that we are looking for the change in enthalpy, and the change in enthalpy is always final minus initial. So reactants are the initial and products are the final. So we want the final minus the initial. So you can look up these values in the back of your textbook, and you can also find enthalpy of reaction tables online. Just Google it. These are not values you need to memorize. They will be provided to you on a quiz or a test, but you will be able to look them up for your homework and your practice. So I would recommend that you refer to the video I have posted on solving number 9 on your chapter 5 worksheet. I talk about a little bit more in depth how you use this equation. And one of the things you have to factor in is the stoichiometry. If there's 1 or 2 or 3 or more of each product or each reactant in the balanced chemical equation. We can also measure the delta H of a reaction by working in the lab and taking measurements. In this case, we would measure temperature changes and combine it with the Q equals SM delta T equation, or and the fact that the delta H of the reaction is the heat divided by how many moles of reaction produced that heat. I don't know where you got to in lab this semester, if you were able to do the coffee cup calorimetry lab in class or not before we ended up remote learning. But if you did get a chance to do that coffee cup calorimetry, you probably used some of these equations in, it's so hard for me to write with this mouse. So bear with me. Coffee cup. Okay, so that's terrible. But anyway, so you may have used some of these equations in lab. All right. I would recommend that you watch the YouTube video I have posted on energy and chemistry, crash course chemistry, video number 17. And there's also a crash course chemistry video posted there on enthalpy. These videos move a little bit fast. You can try to take notes while you're watching them, but you probably have to pause a lot. And they go a little bit more in depth than what we've covered in class, but I really enjoy them. I think they're great illustrations in the videos, and he explains things in a way that's fairly similar to the way I explain things. So you might enjoy his videos, but just be aware that they move fast and they do cover a little bit more than what we are covering in course. All right. Um, After you're done watching this video, please go try problem number 9 on your worksheet. And that wraps up all the video coverage I have for chapter 5. You should be able to, at this point in time, do all of the problems in your study and problem set. And you should keep practicing and be ready for our quiz on Friday and our exam on Monday.